Welcome to Units Raised to Powers 1. In this video, we'll recap the rationale for this new skill of ours and take a look at one example problem. All right, so in class we had looked at these choices. We were going to start with a true relationship because that's what we need for dimensional analysis, and we were looking at these sort of different variations on that original true relationship of 12 inches equals 1 foot. So pause the video if you want to kind of review and recap for yourself and decide if each of these statements is true or false, given that we know that 12 inches equals 1 foot. All right, so here are the results in orange there on our screen. So the first statement remains true. We've done the same thing to both sides of that equation. So again, as long as we're going to do something fair, follow those rules of algebra, that statement will still be true if we do exactly the same thing to both sides. Right? In this case, we've multiplied both sides by 2. The second statement is false because we did not do the same thing to both sides. What we did in that case was just move the units around. And that changes the meaning of that statement. So it is no longer a true statement. In the second one, we have again divided both sides by 12. So we end up with 1 inch equals 1/12 of a foot. So that remains true. We've done the same thing to both sides. We've divided both sides by 12. The statement D, the fourth one, is false. It looks like it wants to be true, but again, take a look at what happened to both sides. And on both sides, we squared only the unit. So we only squared a portion of each side. So that doesn't keep that statement true. So just changing the units to squared units without affecting the numbers as well is going to make that statement then false. Okay, and for the same thing happens in the next statement there, part E. In that case, only one of the sides was cubed. It looks like just the right side was cubed. So 1 foot went to 1 cubic foot, but that didn't affect the side that had the inches on it. So we again did something only to one side and not to the other. So that statement is now false. And the last statement there, part F, in that case, both sides were divided by the unit of grams, which again is not really clear why we would do that, but again, it's fair as long as both sides are treated in the same way. So both sides were divided by the unit of grams, so that statement is still true. All right. So when we looked at this in terms of, well, what are we going to do with that information? What are we going to do with a relationship that we are allowed to adjust? And the answer is it's going to be helpful for us because the units of primarily volume, but area and volume come about from combining or multiplying together units of length. So we've been working with units of length. All sorts of units of length, meters and centimeters and miles and kilometers and feet and inches. All of those are units in one dimension. But of course, we live in 3 dimensions, and a lot of what we're measuring are volumes in chemistry. So to make that conversion, right, to go from a length to a volume, we're going to look at our pictures of our boxes here. And in terms of a volume, the length times the width times the height for a nice rectangular shape is going to give us the volume. So here we have in our diagram something that's 1 foot by 1 foot by 1 foot, which means it's also 12 inches in one dimension and 12 inches in another dimension and 12 inches in the third dimension. So when you think about that and can kind of see and visualize it, you can see that just because 1 foot equals 12 inches, it does not mean that 1 cubic foot only contains 12 cubic inches. It's going to contain 12 times 12 times 12 cubic inches. So in order to make that conversion factor, that was true, 1 foot equals 12 inches. In order to make that work in 3 dimensions, we're going to have to make an adjustment by cubing or raising to the 3rd power everything in that relationship to keep it true. So we'll cube the 1 foot side, and we'll cube or raise to the 3rd power the inches side, right? Number and unit, and we'll end up with 1 cubic foot equals 1,728 cubic inches. And we can do this with any conversion factor and any units that we need to. It's going to, again, typically happen for volume units for us. All right, so this is, in fact, our new superpower. We have the power, the choice, to adjust any conversion factor that we have that's originally true. We can change it so that it includes the units that we need for that particular problem. So sometimes we know the conversion factor in 1 dimension, but we need it in 2 or 3 dimensions. So we need to square or cube it to make those adjustments. We don't need to use it all the time, though. So we saw some examples already where we did not need to use that power, that ability to change things by squaring or cubing all the time, right? We needed it maybe in part of the problem or not at all in the problem, depending on the conversion factors that we already know and the conversion factors that we're going to be using in that problem. So let's put that into practice here. We'll try with this problem. So we have a small weather balloon, have a volume of 61 meters cubed. And we want to know what this volume is in units of milliliters. Okay, so we start with a volume that is in cubed units, meters cubed. So a meter on each side, there's 61 of those. And we want it now in a volume unit, milliliters, that does not contain a cubed unit. Right? The milliliters already represents a 3-dimensional space. The meters cubed represents also, in a more obvious way, a 3-dimensional space. We're going to need a connection here between volume units that are cubed and volume units that don't need a cube, that already represent a 3-dimensional space. And we do have that. That's one of those conversion factors we're supposed to memorize. And it's that 1 cubic centimeter, 1 cc, 1 cubic centimeter, is equal to 1 milliliter, 1 ml. So that is something we expect you to memorize in our class. And it's also one that's easy to forget, but it is our connection between volume units that come from length times width times height, from linear measurements like meters and feet and inches and centimeters. Cubed, it goes from those kind of units to the kind of volume units that already represent a 3-dimensional space. They don't have a cube in their name, in their symbol. So somewhere in this problem, since we have that relationship and going from cubed units to not cubed units, we're probably going to need to use that conversion factor in there somewhere to get from cubic centimeters to milliliters. So now we can kind of think about, well, that's great. That's kind of how the end of the problem looks. How does that beginning of the problem look? Can I get from cubic meters into cubic centimeters? And the answer is, I think I can. Because we know how meters and centimeters are related because we know our prefixes. But these units are cubed, right? So when we look at that conversion factor from centimeters to meters, right, that's only in 1 dimension. And we are looking at cubic meters and cubic centimeters. So this is where we need to use that power. So we need to change our conversion factor from units in 1 dimension, in a linear sort of way, to units in 3 dimensions, in cubed units. And we can't just put a cube there on those units, right? We have to adjust the entire conversion factor so that it stays true and we can use it. When you look at the second conversion factor, right, we're going from cubic centimeters to milliliters. Those are the units that are already present in that conversion factor. We don't need to make an adjustment there at all. We don't need to cube it anymore. It already contains the right units for us. All right, so we're going to have to use our power to cube, right, raise to the 3rd power, that first conversion factor, but we're not going to do anything to the second one. It's already got the right units for it. So when we set up our problem, we have 2 steps, right? The first step is the one that requires us to adjust the conversion factor that we know from centimeters to meters so that it will be then relating cubic centimeters and cubic meters. Okay? And then our second one we're going to use as is. As before, we're going to let the units tell us which part of that relationship goes on the top and which one goes on the bottom. So we still have to watch out for that and make sure we keep the right number part, that right size with the right unit. Okay, so we've got them all set up there. The next important thing to watch out for in these sorts of problems is make sure that you do the math. Don't forget that you're supposed to raise to the third power everything that's inside that first parentheses and not raise to any power any of those other values that we're using, right? They are already in the right form for us. Okay, so carrying out that math, it's always a little tricky, again, when we have powers of 10 in the denominator and we're using raising things to different powers. So make sure you can, again, operate your calculator correctly on these sorts of problems. All right, and our units are canceling out there. So we have cubic meters. We'll cancel the cubic meters once that 3 outside the parentheses is accounted for, and our centimeters cubed, right, which will come about because we cube things in that first conversion factor, and our centimeters cubed that are already present in our second conversion factor will cancel out, and we're left with just milliliters in this case. So we end up with a value that our calculator gives us, but we need to double check on significant figures here. So our starting value has 2 significant figures. The conversion factors we used are all from definitions, right? So 1 cubic centimeter equals 1 milliliter is a definition with no uncertainty. So infinite significant figures, and our prefixes also from a definition. So infinite significant figures. Our answer should have 2 significant figures. You can write it in decimal form or you can write it in scientific notation. That is up to you. That was not specified in this problem. So 6.1 times 10 to the 7th milliliters, or 61 million milliliters. Thank you for joining me for Units Raised to Powers 1. We'll see you soon.